Hello, everyone. Welcome. I'm Dimitri Kazaris. I'd like to tell you about some new work on mass and general relativity. What I'm about to present is joined with Hugh Bray, Sven Hirsch, Marcus Curie, and Daniel Stern. You could view this talk as kind of a continuation of Daniel Stern's talk. I will reference his ideas without explaining them in depth. So if you have not already, could be a good idea to see his lecture. And before I begin, I'd like to thank Christina Fermani and the organizers. It's not lost on me the amount of work that went into producing this conference. Okay, so let's begin. So generally, what I'll talk about today takes place in the context of general relativity. Supposed to be a model for gravity, and the main object you study is a Lorentzian four-manifold. Here it's a metric on, topologically, R3 minus a point across R, the last factor, interpreted as time. Here's the form of the Lorentzian metric for this Schwarzschild example. Should be a minus sign in front of the dt, it's Lorentz signature. So for any real parameter m, you can write down this metric. If you go far away from the origin in the Euclidean 3 space, this metric converges to, this 2m over r terms become very small, and this whole thing converges to Minkowski, flat Minkowski space. So asymptotically, this resembles a flat space. Okay. So this is going to be kind of the area that we're zooming in on today. We're going to be interested in objects like this, not only objects like this, but spatial slices within them. So Coda mentioned one submanifold, hypersurfaces, inside of these Lorentzian objects, which resemble flat space near infinity. I'll tell you what that means in a moment. Okay, so these are called the kind of initial data sets. You can think of the problem of evolving some given state of the universe in time, and then the spatial slice would be like an initial data set. So the relevant quantities here are the metric G, which is H restricted to M, and K, metric 2 tensor, being the second fundamental form of this embedding. And generally, you don't study just any Lorentzian manifold. Should be physically reasonable. So there's another condition that you require out of your Lorentzian manifold, and then that descends to a condition on your spatial slice. It's called the dominant energy condition. I'll tell you about that in certain cases as we go through here. Okay, so this is the object that we're going to be interested in. These Riemannian slices within a Lorentzian four-manifold. Okay. So let us focus further and simplify the picture a little bit. So now let's go to what's called the time-symmetric case, the case where the second fundamental form of the three-manifold, which we were imagining being embedded in a Lorentzian four-manifold, vanishes. It's kind of time-symmetric, second fundamental form, 0. Okay. So what we're looking at is, we could just kind of forget about the Lorentzian manifold at that point, and we just have a three-manifold with a metric G, and we require that it's asymptotically geometrically close to Euclidean space. And what does that mean? So you imagine M could have some topology here, or maybe it could be even having a boundary. What we require is that there is some compact set K and a chart from M minus K to Euclidean space minus some ball. Or maybe, the manifold has many ends, but let's take a look at a more basic situation where there is just one end. Okay, so this is some diffeomorphism between M minus the compact set and R3. So this gives you coordinates on this part of your manifold. It's called charted infinity. And so this gives you coordinates x1, x2, x3, taken from Euclidean space. And in these coordinates, we require that G, the Riemannian metric, decays to the flat metric in the following sense. So G minus the flat metric on R3 should behave in these coordinates like, say, R to the minus 1. And also derivatives of G should behave as derivatives of R to the minus 1 behave. So R to the 2 and 2 derivatives, we also require R minus 2. Okay, so that is the asymptotically flat condition. You have a charge infinity where you have decay to the flat metric. Okay, and then I said there is an extra condition that you require on your 4 manifold, which descends to a condition on your 3 manifold. In the case that k is 0, this condition just becomes the non-negative condition on scalar curvature. Okay, scalar curvature is interpreted as a kind of local energy density in this context, for the gravitational field, and this is a physically reasonable assumption. Something like the density is non-negative. So you have these 2 conditions on this 3 manifold. It's asymptotically flat at the end, and curvature condition. Scalar curvature is non-negative. As we know, having a metric with non-negative scalar curvature is a very weak condition. It's a pretty flexible condition, tells you very little about the underlying geometry of the manifold. But then you throw in this extra condition that you must decay to the flat metric. There's some slight tension there. And geometrically, this is captured very well by the following numerical invariant called the mass of the manifold. It's called mass. It has some interpretation in terms of the physics going on. But abstractly, we could think of it as the following expression here. So, as I was defined before, you have your asymptotically flat 3 manifold. M, you have this charge infinity. The charge infinity gives you a foliation of your end by spheres, by going out, radius r in the coordinates that you have. Okay, that's what I mean by this SR here. So you integrate this following expression in the metric tensor, first derivatives of the metric tensor, over these spheres and take the limit of the spheres go to infinity. So if you're not familiar with, if you haven't thought about these notions before, it could be a bit strange looking. Usually if you could choose whatever coordinates you wanted, these derivatives don't carry any information. Point-wise, they carry no information. But somehow when you integrate over the sphere and these preferred coordinates, which make your metric decay to the flat one, this gives you a quite subtle invariant. And maybe more geometrically, you could think of this as the following. The following doesn't totally make sense. The topology of M is not R3, but you can think of it in the following way. So suppose you look into the space of all metrics on R3, some large, big space. You have the flat metric on R3, and then you have this metric G at the, in the non-compact end. Okay, so we have the scalar curvature map, which takes a metric and sends it to, the smooth function on M, being the scalar curvature. You take the derivative of that map. That's what I mean by dr here. So if you take the linearization, the derivative of the scalar curvature map at the flat metric in the direction of whatever metric you have on your manifold, you integrate that over the entire manifold of the divergence, so mostly, and so you'll get a boundary term. This boundary term is what's inside this integral over the sphere radius r here. So you can think of it that way. It measures kind of the deviation from the flat metric in that sense. What would we like to say about this? So it's kind of a numerical invariant that captures a lot of this tension between these two, the asymptotically flat condition and the scalar non-negative condition. Physically, you would want the following to hold. If scalar curvature is non-negative, if the local energy density is non-negative, then the mass of, the total mass of the system should be non-negative as well. This is called the positive mass conjecture, and it's been proven in this context by a number of different methods. So first proof through the Shane and Yao in the late 70s, early 80s. Witten produced a proof soon after using spinors, very different method than Shane and Yao. But also there's proofs, techniques that apply more generally, but in particular prove the Riemannian positive mass theorem through Huisken-Elman, Bray, and more recently by Yu-Li. Okay, so again, it says, if you are in the above context, you have this asymptotically flat initial data set with K vanishing, and you have this curvature condition, the dominant energy condition, scalar curvature is non-negative, then the mass of your manifold is non-negative. And if you have multiple n's, then for each n, this quantity is non-negative. You can imagine doing this integral not over spheres of one end, but over another end. Anyways, it comes with a very important rigidity statement, which is if the mass of your n vanishes for some n, then your whole manifold is just R3 with the flat metric. Very, very remarkable theorem to kind of pick out flat space among all manifolds with scalar curvature non-negative. There's really nothing else like it. For Ricci curvature, if you just think of that as in terms of curvature conditions, the non-negativity of Ricci curvature, you have other tools at your disposal, like splitting theorems. If you have a line that the manifold splits. But for scalar curvature, this is kind of one of the more remarkable statements you can make in this direction, splitting direction. Anyways, let me continue. Okay, so suppose you have your asymptotically flat manifold. Again, you have a chart at infinity. This gives you, the map to R3 minus the ball. And in this chart, consider some linear function. Call it L. And for simplicity, let's just think that its derivative is norm 1. Here is what we prove. So in this situation, where you have L, you have a manifold M3, asymptotically flat. Here we don't need, so you don't require scalar curvature non-negative. This theorem applies regardless of what scalar curvature is. There is a canonical harmonic function on a portion of your your manifold, which is asymptotic to the linear function that you prescribed. That's one statement. There exists such a thing. And then here is what it says about the mass. The mass of your manifold is bounded below by 1 over 16 pi. The integral over the region where this thing is defined, this harmonic function is defined, called the exterior region of M, of the Hessian squared norm divided by the gradient of U plus the scalar curvature of the manifold times the gradient of U. Is the bulk integral integrated over the whole three-dimensional space exterior. Okay, so immediately, if you saw Daniel's lecture, this right-hand side will be pretty familiar to you, which gives you a hint as to how we prove this, which I'll explain in a moment. But notice as a corollary to this, you get the positive mass theorem. If the scalar curvature is non-negative, if you impose that extra condition, then the right-hand side is clearly non-negative, so the mass is non-negative. But this is one step further than just proving the positivity of something. This is practically a formula. In fact, there's another quantity I could write here, which is non-negative, which would make this, at least heuristically, an equality, just a formula for mass, which is pretty rare. the original proof by Shane-Yao did not give a formula for mass, just proves that it was a proof by contradiction, just proved the positivity of mass. Witten's proof gives you a formula for mass, but it requires scalar curvature non-negative in this context. All right. So again, to be clear, this bound, it does not require any curvature condition. It requires the mass to be well-defined, which is like the scalar curvature should be in L1, but that's all it requires, asymptotically flat and mass being well-defined. Also, this works if you have multiple n's or if you have a boundary to your manifold. In that case, then, to obtain this harmonic function, you would impose a Neumann condition to your harmonic function, and the formula still works. Still gives you a lower bound in that context. So, I mean, just as a little toy picture, here you could imagine your M, and then you could imagine, as a graph, you have your function. It does something in here, and it's asymptotically, say, asymptotic to a linear function. If you imagine this graph as I've drawn here, it would be like this three-dimensional plane. Okay, so there are some remarks you can make. Okay, so if you think about this harmonic function, it relates to the two original proofs of the positive mass theorem. For instance, if you think about the Shane-Yao proof by contradiction, they construct and analyze very carefully a single minimal surface. This is to be compared with the foliation one obtains from this harmonic function. If you take the level sets of the harmonic function, called a sigma t, so u inverse of t, gives you some sort of singular foliation you can kind of imagine. This could be compared with a minimal surface. So instead of kind of analyzing a single minimal surface, showing the original proof, you can imagine we're analyzing the geometry and topology of a zillion surfaces, the foliation by the level sets of U. But also you can compare this to Witten's proof. In Witten's proof of the positive mass theorem in this context, under a scalar non-negative condition, he constructs a harmonic spinner, direct harmonic spinner on your 3 manifold, which is asymptotic to a constant spinner on R3 as you go out to the end, appropriately interpreted. So you could compare what we did, this formulation to that formulation, where you would think of the constant, the asymptotically constant harmonic spinner, you would compare that to du. It's kind of a similar object. Du is, as you go out to infinity, that converges to basically, dl, which is like a constant spinner or a constant, one form on R3. So it bears some resemblance to both of these two main methods of proof. Okay, so let me give you a sketch of what's going on. All right, so as I said, we're going to, we did the Smith-Daniel. We're going to follow the kind of computational ideology that he introduced. So let's consider the Laplacian of the gradient of our harmonic function. So, you have some three-dimensional asymptotically flat manifold. Let's ignore this business about the exterior region. I can explain that later. But let's construct this asymptotically linear function u, consider this quantity, and then here's what we should do. We should use the Bachner formula to express this thing in terms of Ricci curvature and Hessian and whatnot. Then we look at that Ricci curvature term, interpret it as the Ricci curvature in the normal direction to a level set. Use Gauss-Godazzi to replace this Ricci curvature by things involving the ambient scalar curvature and the Gauss curvature of the level set, second fundamental form things. Then you integrate this expression, this formula that you got, so integrating this thing, and then you want to use the Fourier formula and the Gauss-Bonnet formula. When you do this, so I'm skipping over a lot here. I wouldn't expect you to follow what I just said, but this is the rough idea behind what Daniel was talking about. Again, I encourage you to look at his talk and look at his papers on this. Very nice read. And so when you do this, you get boundary terms. So you're going to be integrating Laplace of the gradient. So when you integrate that by parts, you get this normal derivative of the gradient. You know, I'm picking some bounded set in your manifold, probably like what's inside the sphere of radius r. Might have some topology here. This is omega, you can imagine. Okay, you'll get one boundary term from integrating by parts. That's clear. And then in the above process, when you use the Gauss-Bonnet, you extract the Gauss curvature of a level set in this manifold with boundary, this this open, this compact domain. And then we use the Gauss-Bonnet formula. We'll get the Euler characteristic, the Gauss curvature, and then the integral of the geodesic curvature of the boundary as a submanifold of the surface, the level set, which is the second term here. So this is what you'll get when you look at these two. You can interpret them both as boundary terms. And this is, the second integral you're integrating over all the values that u takes on omega. Okay, so you'll get some non-negative stuff on one side of the, what I just said will happen when you follow this philosophy. And then you'll be left with these two kind of boundary terms. On the other side of the equation, you have some non-negative stuff like the Hessian and the, the scalar curvature, as I mentioned before. Then you get these two boundary terms. They converge to mass. And it's a detailed calculation. The mass is given by a formula, and you have to show that these two things converge to that formula. But let me just say that these both kind of converge to mass, and it's in a ratio of like this first term has precise but not really applicable or useful sense. Has 2/3 of the mass of the manifold, and this is 1/3 the mass of the manifold. And just to explain the philosophy a little bit, so you have your three-dimensional manifold, and it's foliated by some, the level sets of your asymptotically linear harmonic function. Because your harmonic function is asymptotic to a linear function, its level sets near infinity resemble flat planes, loosely speaking. So you imagine, okay, if you intersect this with some big set, then I'll use a different color here. You have kind of a boundary of sigma t intersect omega that I've drawn in this green here. You'll have another one over here. So the sigma t's, they resemble planes as you go further and further out. So you would imagine that if you intersect with, say, a ball in your manifold, the intersection would resemble kind of a round circle, but not exactly, because your level sets are not exactly planes, and the deviation from being planes is a measurement of the mass of the manifold. Okay, so this difference here, you imagine you get yourself into a situation where the Euler characteristic is comparable to 1. That's the Euler characteristic of a disk. This is about 2 pi. And then you're subtracting off the integral of the Gauss curvature, which is kind of like the integral of the curvature of a circle in a plane, but not quite either of those things. And this is some subtle quantity. This integral of the geodesic curvature is not quite 2 pi, but it's very close, and it contains some mass. So, okay, so that's the loose philosophy of what is going on here. Okay. So that is the next kind of explanation of this theorem for this time symmetric setting that we did with Bray, Curie, and Stern. Okay, so this is interesting, but what is the real goal from the perspective that we started with? We really want to study not just time symmetric, initial data sets, but general initial data sets. And you imagine this lives in some four-dimensional Lorentzian manifold. You'll get not only the Riemannian metric from the restriction of the Lorentzian metric, but you also get second fundamental form, which captures how your spatial slice is twisting around in the spacetime. Okay. Now, instead of just a single quantity, the scalar curvature, kind of controlling the local energy density, there are two quantities of interest. There's kind of, again, the local energy density, and then something which encaptures how your manifold is being twisted in the spacetime. So you have this mu and j. The dominant energy condition now being articulated by the inequality mu is less than or equal to the norm of j here. Okay, and now there are, the mass in this context splits into two pieces. The energy, as kind of roughly measured by mu, and the momentum. And there's three different momentums for the three different directions you could be rotating about. Okay, they have some expressions here as I'm showing you. Let's not worry ourselves with understanding them completely if you're not familiar with this. And if you are familiar, you didn't need me to tell you this anyway. But let's go on. So in this context, the physically reasonable, the conjecture is the following. You call it the full positive mass theorem. Originally proven by Shane and Yao, and also later by Witten. Depending on how you think about it, before or after. Anyway, so in this context, with the, if you have an initial data set with a non-zero second fundamental form K, and you have the dominant energy condition, again, interpreted something like non-negative local mass or energy density. Then these two quantities are, these two global quantities are related in the following way. E minus the norm of P, P being, having three quantities, and you take the Euclidean norm of that, should be non-negative. Moreover, if you attain equality for some n, you could also measure this for each n. Not so important now. But you attain equality exactly in the situation where your manifold, your initial data set, came from being some spatial slice of flat Minkowski space. That is the full positive mass theorem, you could say. Okay, so we try to approach this problem as well. We had some success with the Riemannian version using these kind of asymptotically linear functions. I should say something in this context as well. And when you think through these thoughts carefully, you see some interesting things. Okay, so here is the right context to work in. Okay, so you're imagining that M sits inside of some four manifold. Four, here's your M here. So if you have a function on M, the three manifold, then you can consider the following kind of, well, the natural operator, which we call the spacetime Hessian, which is given by the regular spatial Hessian of U, but then you are twisted kind of by the second fundamental form with the embedding of M into the Lorentzian manifold. And where does this arise? So the inspiration comes from Witten's proof of the positive mass theorem, where in this context of having a three manifold inside of the Lorentzian four manifold, he looks for a spinor, which is Dirac harmonic, but not using the Dirac operator from the Riemannian structure of M, but also incorporating the second fundamental form. So basically kind of taking the connection from the ambient four manifold and making a Dirac operator from that. that's kind of what we want to do in this setting as well. You want to take your operator on M, but kind of that you used in the Riemannian setting, but twist it by K in some way. And here's the logic that kind of directly connects you to the Witten argument. So the space-time Hessian is, you can think of it in the following way. Imagine you have a function on the whole Lorentzian 4 manifold. So, U bar on the whole 4 manifold. Now, take its one jet. Okay, so just remember the first derivatives. And then you restrict that to the M. So, you know, it's like this one is what I say is one jet of the restriction of U bar to M. So that remembers everything about M. So all derivatives, everything in the M direction. But only remembers one derivative in the normal direction. And if you also assume that your U bar in this mind game has a null gradient, so its Lorentzian length is 0, then this is an example, or sorry, this is what the space-time Hessian is. The Hessian of the restriction for such a function with a null gradient, which is you know, you could directly compare to what happens in the Witten proof. Okay, now you play the same game, but instead of the harmonic map equation, you solve this PDE, which is, you know, it's the trace of the space-time Hessian above. So you solve the equation Laplace U plus trace of the second fundamental form, and the mean curvature of M3 inside the Lorentzian manifold, times the gradient of U. That should be 0. And we should also require that it's asymptotic to some linear function with you know, derivative as norm 1. The model being something like a null coordinate in Minkowski space, like x plus t. This is such a function. It's you know, so you know, U bar be x plus t. This is something which has a null gradient measured with the Minkowski metric, and you know, the wave operator, the Minkowski space like the U bar, is obviously 0. And its derivative, the second derivative in the normal direction vanishes, so you could restrict such a thing to some Riemannian slice inside Minkowski, and you would get a solution to this equation. So you can interpret this as kind of, if you look at the level sets of this function, it's like you're scanning, you know, you got your M in here, the N, and then you can imagine, this is not how you solve for such a function, it's not how you solve the PDE, but you can imagine what you're doing is you're taking a bunch of null planes in your ambient manifold, and intersecting them with M, and these give you level sets of the solution of U. So it's kind of like you're scanning your initial data set by null planes, you could think. That's kind of the loose philosophy. Okay, and this is the right differential equation to solve to obtain the following theorem, which is joint work with Sven Hirsch and Marcus Curie. So in this context, you have your, you know, fix some end of your manifold with your initial data set with the G and the K and some linear function at infinity. Then you can find some space-time harmonic function. So that means you're solving this equation, not harmonic, but that operator vanishes. Defined on some manifold, which locally, I mean, it models the original thing you're starting with. Call it exterior region, but it's a more, I don't know, it's a different sort of object. You construct it from the initial data set, but it's not so simple. But anyway, so there's a function defined on some space so that the energy plus the inner product of the linear momentum with your, you know, the linear momentum vector with your linear function that you're asymptotic to is bounded below the following quantity. So it's very similar to the first bound for mass. By the way, this, if you take A to be basically minus P, then this gives you the desired positive mass theorem. If you take A to be the direction where, the direction of P and minus P, then you get the theorem. The only difference being from the Riemannian time symmetric case is that instead of just scalar curvature, you have this mu minus j, which of course reduces the scalar curvature in the case when k vanishes. And notice that instead of the usual Riemannian Hessian coming from G, you have this space-time Hessian appearing on the right-hand side of the, in the bulk integral in the lower bound. Okay, so as a corollary, you get the full Riemannian, or not just Riemannian, it's the whole space-time positive mass theorem, which is very interesting, and it's good. Having a proof of the full positive mass theorem is a little bit more of a rare thing than having a proof of the Riemannian one. And so, yeah, so there's not a, this kind of makes the comparison between, du, the kind of asymptotically constant one form du, and the Witten spinors a little bit more convincing, since it works in this context as well. Okay, so let me make a full, a couple of comments here. First of all, this is, there are other proofs of the positive mass theorem, but some of them, for instance, the original Chain-Yau proof required a little bit of extra decay on the second fundamental form than you would necessarily think you need, and our positive mass theorem is top of the line in terms of generality, in terms of the assumptions you need to make on G and K in order to make it work. That's just one comment. It ties Witten for the best positive mass theorem in that dimension. Okay, now let me the main point I want to make before I end, the following two features of this formula, which are not just abstractly good, but are specifically good. Okay, so the two features are, it is a estimate, which is basically a formula. If I added some complicated term involving the Euler characteristic, it would have been an actual formula, but it would have not looked very good. But so it's essentially a formula for mass by means of a bulk integral. And it works, so that's number one, which is, for instance, the original Chain-Yau proof, proof of contradiction, roughly. So, essentially, so you don't get a formula for it. For Witten, you also get a formula for it. However, Witten's formula only applies under the dominant energy condition. The second point, the formula that we get applies regardless of dominant energy condition. So these two properties of our formula allow you to do some very interesting things, which I call something like mass storage technique. And this is part of a work in progress, but here's the, the rough idea of what I'm saying. Why is it a good thing to both have something that applies regardless of dominant energy condition and also gives you a formula for mass. So here's just a Fourier model example. Suppose you have some asymptotically flat manifold MGK. It's not flat at infinity at all. Curvature at infinity. You could do the following, which is usually not a good thing to do, but let me explain. You could just do a, kind of barbaric transition. So you do a cutoff, construction to the flat metric at some distance to make some manifold where, okay, you resemble the original G and K in some compact portion, but then outside of that, you are actually just flat. So you just do some, you grab your metric and you just do some linear interpolation between your metric and the flat metric on some annular region. Let me maybe mark it in orange here. you have some region here, say, AR. You transition at some distance R. Okay, you make such a construction. Why? Well, you can apply. So here, just notice that because we have done such things so unsubtly, the dominant energy condition will definitely fail across this orange region in this annulus. So dominant energy condition fails. I mean, the mass is essentially obstructing you from doing such interpolation anyway. So you couldn't do that anyway. So the dominant energy condition has to fail there. Your manifold's not flat. Okay, and you satisfy dominant energy in the interior. Okay, you make such a construction, and then you apply the formula, the theorem that I just mentioned. You find an asymptotically linear spacetime harmonic function. You apply the formula. You apply the formula. You get something which roughly says, okay, the mass of this manifold, which is 0 because you transition to totally flat outside of the compact set, is done below by, okay, then you have space-time Hessian term. And then you have, u minus j here, integrated over the manifold. And then just ignore the contribution from the dominant energy condition and the interior. And the dominant energy condition, the mu minus j is 0 outside of this annular region. So you can bonus below by just an integral over the annular region, AR, of mu minus j times the gradient of u. Now, what you can do is show, and this is not obvious, but you can show that this thing, this contains the mass of your original manifold. So this limits to basically minus a constant times m. So it's, roughly limits as r goes to infinity, this transition angular region, you get minus m. So which, proves the positive mass theorem for you in a kind of indirect way. But the point I want to emphasize here is that since we can get a formula for mass without dominant energy condition, which is a novel aspect of the theorem, you can see how mass is stored in a compact region using a construction like this. It's kind of a new idea. This is the subject of current work. You can use this idea to study the mass of different types of objects, not asymptotically flat, but other asymptotics. Okay, so that's what I want to emphasize about this work. Let me just say there is a word about the exterior region that I mentioned there. So if you look back several slides here to the sketch of the proof, it involves, so I said you need to get yourself into a situation where this Euler characteristic term is roughly 2 pi. Or in other words, the Euler characteristic of your level sets is 1. You need to get yourself into a situation where that happens. So what you need to rule out, so you don't want it to be big. If it's big, then that kills the inequality. Okay, yeah. Okay, so to ensure this condition that the Euler characteristic of your level sets does not get large, for instance, if you had spherical components to a level set, that'd be bad. The Euler characteristic would then blow up, or be bigger than 1. Okay, so to ensure that doesn't happen, you can just say there's no other, second homology in your manifold. That would ensure that you can't have level sets which are spherical and disconnected from the rest of the level set that has to be kind of like a plane. By using the maximum principle, level set has to be homologically non-trivial. So if you have no homology, then you don't have to worry about that. So you want to kind of kill H2 of your manifold. And what that means is produce some other manifold. So if this is your original one, M. This is what M exterior would be like. You have to kind of geometrically, in a careful way, kill this homology. So you'd have to, you want to excise the analog of minimal surfaces in the Riemannian case in this context. So I don't know, you could imagine it looks like this, where these things are analogs of minimal surfaces in the space-time context, which are marginally inner-trapped or outer-trapped surfaces, MITs/MOTs. Okay, so that's why you have to pass to this exterior region, and it might not be some open domain in your manifold. You might have to pass the covers to use these constructions to kill these MOTs. And let me just be clear, to be a little bit not hiding any technicalities here. This reduction to the exterior region, which has no homology, in order to kill this homology, you need to use the Zhang equation, which is what Sheng and Yao used in their original proof of the full positive mass theorem. So this reduction requires the kind of the same work as in the original proof. Okay. So let me end there. If you have any questions or you'd like to get in contact, let me just leave you my email. Just D and then my last name is f@gmail.com. Feel free to email me with any questions you might have about this talk. And thank you very much for your attention. Enjoy the rest of the conference. Bye.